Hi guys, welcome to my channel. In today's class, we're going to be exploring the introduction to Maclaurin series. The Maclaurin series expansion is defined by the formula. We have a function of x equal to f of 0. So for the Maclaurin series, we'll be substituting x to be equal to 0 into the successive derivatives. So we'll be having f of x to be equal to f of 0. So here x is already substituted as 0 plus we have the first derivative of f of x. So we also substitute x to be 0, then multiplied by x, plus the second derivative of f of x. Substituting x to be 0, we divide by 2 factorial multiplied by s squared, plus we have the third derivative of f of x. Substituting x to be 0, divide by 3 factorial multiplied by x cubed, plus dot dot dot, plus the arrow derivative of f of x, substituting x to the 0 over r factorial, then x to the power r, then plus dot dot dot, because this is actually going to infinity. So the Maclaurin series is a process of expressing a function of x as an infinite series in ascending powers of x. So ascending powers of x will mean x is going from 0 to the power 1 to the power 2 to the power 3 down to the infinite power of x. So now that we know that the Maclaurin series expansion is used to express a function as an infinite series, so we can give an instance like the sine x. So an example is sine x, whereby if we express this using the Maclaurin series, it should give us x minus x cubed over 3 factorial plus x raised to the power 5 over 5 factorial minus x raised to the power 7 over 7 factorial plus dot dot dot. Like I said, this is an infinite series, so this is going to infinity. So we can also have exponential x to be, we'll have 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot 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 x to the r over r factorial plus dot dot dot. So this is also going to infinity. So now this is the Maclaurin series expansion of sine x, and this is also the Maclaurin series expansion of exponential x. So now we need to derive this. We need to derive this Maclaurin series formula. It needs to be derived. Now let's move to the next page and see how this is done. Now we have given that f of x can be differentiated infinitely many times, and that it is a series expansion of the form. We have a function of x to be equal to summation r going from 0 to infinity ar times x raised to the power r. So for this, we have r to be equal to 0, 1, 2, 3, 4 down to infinity. So now expanding this power series, this summation r going from 0 to infinity. So if we substitute r for this series to be 0, 1, 2, 3 down to infinity, we should be having a function of x to be equal to a0 x raised to the power 0 plus a1 x raised to the power 1 plus a2 x raised to the power 2 plus a cubed x raised to the power 3 down to infinity. Now, where all AR, that's when I mean AR, I'm talking about A1, A0, A2, A3, where all of these are real constants. Now we have to show that the series expansion, we have to show that this series expansion in yellow must be the Maclaurin series expansion. We have to show that this must be this. Now, how do we do this? So we are given this function to be equal to the power series f of x is equal to, so I'm going to rewrite this as a naught because x raised to the power 0 is 1. So a naught times 1 is a naught, plus we have a1x plus a2x squared. We have a3x cubed. We have a4x raised to the power 4 plus dash dash dot plus ar x raised to the power r plus dot dot dot. Okay, now, so from this explanation here, we can see that it says given that f of x can be differentiated infinitely many times. Now, meaning that this function f of x, which is expressed as a power series, can be differentiated infinitely many times. That means we can get the higher derivatives of f of x starting from the first derivative, the second derivative, the third derivative down to infinity, because it says differentiated infinitely many times. So another thing we should take note that for Maclaurin series, x should be substituted as 0. I stated that earlier, that x should be substituted as 0. So the first thing we have to do is to get the constant a0, a1, a2. So we are trying to get the constant a0, a1, a2, a3, a4, ar down to infinity. Now, for we to get this constant a0, we have to differentiate infinitely many times. But before we differentiate, let's look for f of 0, because it says substitute x to be 0. Now we are giving f of x as this. Now substituting x to be 0, we're having f of 0. Now this is from the function, which is equal to the power series. So this is going to give us a0. There is no x here, so we'll move to the next one. a1 times 0 plus a2 0 square plus a3 0 cube. I'm going to put infinity here because definitely if we multiply the zeros to the constant a1, a2, a3, that's going to give us 0. So a0 plus, we have 0 plus 0 plus 0. So f of 0 is equal to a0. Now from this, we can see that we've gotten the constant a0, it is equal to f of 0, because f of 0 is equal to a0. So the constant a0 is equal to f of 0. So just like I said, for we to be able to show that this function, which is equal to the power series, can actually be the Maclaurin series formula. So like I said, we have to look for the constants a0, a1. So we've been able to get a0 as f of 0. The next thing is to get a1. Now for we to get a1, we have to differentiate. That's, we look for the first derivative of f of x. Now the first derivative. So if we are to differentiate, we know that the formula for differentiation, I would love to give us the formula for differentiation before we start differentiating. If we have y to be equal to ax raised to power r, so the derivative is going to be dy dx equal to r, that's this r which is the power, we multiply by this function ax raised to power r, then we're going to subtract 1 from the power. So now this is derivative. If we are given a function y to be equal to axr, so we are differentiating with respect to x. So that should give us dy dx. Dy dx equal to the power r multiplied by ax raised to power r. Then we're going to remove 1 from the power. So I would love us to take note that the derivative of a constant is always 0. So now let's start by looking for the first derivative of f of x. Now, from the previous slide, we have that dy dx is denoted as the differentiation of y. So we can also write this as y prime. So in this case, we have f of x. I'm going to write this as f prime of x. So f prime of x is the first derivative of the function f of x. Now this is going to be equal to, if we are to differentiate, a0. a0 is a constant. The variable x is not attached to this. So the derivative of a constant is 0 plus a1x. The power here is 1. So 1 times a1x should give us a1x. Then 1 minus 1, you know we have to remove 1 from the power. That's the formula for differentiation. So 1 minus 1 is going to give us 0. Now we have plus 2 times a2 x raised to the power. If we remove 1 from the power square, it remains 1. Plus, here we have 3a3 x raised to the power 2 plus 4a4 x raised to the power 3 plus dot dot dot. I don't want to take it to the arrow order, so let's just stop with the number, so it's going to be easy for us. So dot 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 is denoting that this goes to infinity. So now that we've been able to do this, remember we are substituting x to be 0. So, but before we do that, this f prime of x is equal to, we have 0 here, then we have a1, x raised to the power 0 is 1, n raised to the power 0 is 1. So we have a1 plus 2a2x plus 3a3x squared plus 4a4x cubed plus dot dot dot. Now this is f prime of x, but we are substituting x to be 0. So this should give us f prime of 0 equal to, we have a1 plus 2a2, then we have 0 plus 3a3, then we'll have 0 square plus definitely 0 cube is also 0. So let's just keep it like this. Now the f prime of 0 is equal to a1 because this is 0, this is 0. Multiplied by 0 is 0, multiplied by 0 squared is also 0. So f prime of 0 is equal to a1. Now we've been able to get the constant a1. So the constant a1 is equal to f prime of 0. I hope you remember that we've been able to get a naught also. The constant a naught is equal to f of 0. Now the constant a1 is equal to f prime of 0. Now let's get the second derivative. So for the second derivative, we're going to be differentiating this. This is the first derivative. So if we differentiate it again, it gives us the second derivative. So this is how we work on higher derivatives. So if we differentiate this again, we get the second derivative. Now second derivative is going to be denoted as f prime prime. So we have f prime prime of x is going to give us a1 is a constant. So that's 0. Derivative of a1 is 0 plus we have 2a2x. So there is power 1 here. So this should give us 2a2 x raised to power 0. Then we'll have plus the power here we'll have is 2. So 3 times 2 a3 x raised to power 1 when we remove 1 from square. So plus 4 and then here we'll have cube. So multiply by 3 a4 x raised to power 2 plus dot 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 infinity. So f prime prime of x is equal to, this is 0, so we are left with 2a2 x raised to power 0 is 1 plus 3 times 2 a3x plus 4 times 3 a4 x squared plus dot dot dot. Now substituting x to be 0, we have f prime prime of 0 to be equal to 2a2, so 2a2 plus 3 times 2 a3 times 0 plus 4 times 3 a4 times 0 square plus dot dot dot. So that should leave us with, we have f prime prime of 0 to be equal to 2a2 because this time 0 is 0, this time 0 is also 0. So now we need to look for the constant a2. So in this case, a2 is equal to f prime prime of 0 divided by 2. Because when we divide both sides by 2, a2 is left alone, which is equal to f prime prime of 0 equal to 2. So we can actually write this as f prime prime of 0 over 2 times 1, which is equal to f prime prime of 0 over 2 factorial. Now we need to get the third derivative. So for the third derivative, we'll be differentiating f prime prime. So differentiating, we'll be having f prime prime of x equal to, this is a constant, so this is 0 plus differentiating here, there's a power 1 here, so this will give us 3 times 2 a3 x raised to power 0 plus 4 times 3, then there's a power 2 here, times 2 a4 x raised to power 1 plus dot dot dot. So that leaves us with f prime prime of x equal to 3 times 2 a3 x raised to power 0 is 1 plus 4 times 3 times 2 a4 x plus dot dot dot. So now we need to substitute x to the 0. So f prime 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 of 0 is equal to 3 times 2 a3 plus 4 times 3 times 2 a4 times 0 dot plus dot dot dot. So this is equal to 3 times 2 a3 because if we multiply this by 0, it is gone. So 3 times 2, A3. Now we need to look for A3. A3 will be equal to f prime 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 of 0 over 3 times 2. So we can actually write this as f prime 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 of 0, 3 times 2 times 1. So it gives us f prime 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 of 0 over 3 factorial. So we can see how we got that, dividing both sides by 3 times 2, dividing both sides by 3 times 2, which gives us A3 to be equal to f prime 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 of 0 over 3 factorial. So I think we can actually stop here, though you can get the fourth derivative, the fifth derivative, sixth derivative, but the whole point is we are going to infinity because this is the Maclaurin series. So therefore, we've been able to get A0 to be equal to f of 0. We got A1 to be equal to f prime of 0. We got A2 to be equal to f prime prime of 0 over 2 factorial. A3 is equal to f prime 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 of 0 over 3 factorial. So we can see the pattern that A4 will be fiv of 0 over 4 factorial. A5 will be the fifth derivative of f of x, then x equal to 0 over 5 factorial, dot dot dot. We can say AR will be the rth derivative of f of 0 over r factorial down to infinity. So now we've been able to get the constants A0, A1, A2, A3, A4, A5. So we're going to substitute that into this function, into this. You can come here and see the function I'm actually talking about, this particular function in yellow. We're going to substitute the constants A0, A1, A2, A3. So we'll be able to get the Maclaurin series. Now we'll be having f of x is equal to, so from what we derive, we can see that A0 is equal to f of 0. So this is equal to f of 0 plus, we got that A1 is equal to f prime of 0. So this is f prime of 0 times x. We have this x here. So plus A2. For A2, we have f prime prime of 0 over 2 factorial. So we are multiplying by x squared. Plus for A3, we have f prime 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 of 0 over 3 factorial multiplied by x cubed. So we are multiplying by this x cubed here. Now for A4, we'll have the fourth derivative of f, substituting x to the 0 over 4 factorial times x raised to the power 4 plus dot dot dot. Then for the r order, we'll have over r factorial, this is of 0, x raised to the power r plus dot dot dot. So now we can see the function of x, which is in power series. We've been able to derive the Maclaurin series from it. This is the Maclaurin series. We've been able to derive the Maclaurin series from that function. Now that we've seen how the Maclaurin series formula is derived, we should get used to the formula, because in our next video, we're going to use this Maclaurin series to find a series of other functions like exponential x, sine x, cos x, the natural log of x plus 1, and so many other functions we might want to work on. So this is the Maclaurin series formula. Thank you very much for joining me in today's class. Do not forget to like, share this video, and subscribe. Bye.